Okay, so let's continue. So we are discussing the magnetostatics and all the effects, the magnetic effects that are exposed through the application of the magnetic field. So that's what we are studying right now. So we started the analysis of magnetic field from the postulates, where one of the postulates was the divergence of the magnetic field, which is zero, and the other one, it was the curl of the magnetic field, which is mu J, where J is the current density. Then we discussed the Biot-Savart law, and the Biot-Savart law, where we find the magnetic vector field A and the magnetic potential, magnetic vector potential A and the magnetic field B, using the same or similar expressions. And now we also, in one of the previous sessions, we studied what was the magnetic field for a loop that was carrying a current I. And we found what was magnetic field at some point here, where because of the symmetry, the problem looked relatively simpler. But we also found what was the magnetic field at some point P here of this vertical axis, where the magnetic field can not be as in here. So if we had this point right on top, this would be the magnetic field. But if we go at some other point P, away from the theta zero angle, so this theta is different from zero, we get a different vector answer for the magnetic field. Then, in this case, once we found the magnetic field here, we considered what would be the magnetic field if the B was much smaller than the R, okay? So the magnetic field, whenever the B, where the B is the radius of this one, this would constitute a magnetic moment, or a very small loop of current, which creates a magnetic field at some distance. Now, that was the beginning of our introduction of the magnetic field, or the magnetic dipole. The magnetic dipole, we found out, this was recorded, sorry, it's a vector. So this vector A, this is equal to A phi, so it has a symmetry of A phi, mu 0 I d squared over 4 pi r squared, where r is this distance times, let me check, so this is times sine theta. Now, if we have a look here, we know that the A, it should be with the direction of the current. And if the coordinates here are the cylindrical coordinates or even spherical, the current is going along the A phi. So we know that A phi for cylindrical and for spherical coordinate system is this way. So if the current, it can be written as I times A phi, this shows that we have a circular current. Then A should be the same, because we know that A, or dA as a vector, is equal to mu 0 I over 4 pi dl over R, where dl is a current. So it's easy to notice that the current has this direction of A phi, and immediately we can also conclude that this should be also the A. But if this is the A, then last time we wrote this equal as mu 0 times m, where this is the dipole moment, or magnetic dipole, cross AR, and AR, we can note this one in a moment what AR is. AR, it's equal to, so these are a couple of notes, but as a reminder, AR is equal to the vector R divided by the magnitude of R. So that's AR. And then here, we have the opportunity to define a new quantity, which is a magnetic quantity, which is equal to AZ times the I pi b squared. So this is in principle the surface area of the loop. So if this is a small loop, we're going to have that this is again equal to AZ times I times the area. Okay. So once we have these definitions of the magnetic moment, we move on and we define a new quantity which is called the magnetization. Now, magnetization is defined as the volume density of magnetic dipole moments. So this is a little m, and here we can define the next important vector, which is the capital M, and this is defined as the summation over all of the dipole moments, mk, over per unit volume. Okay, so this is really density of magnetic dipoles, magnetic dipoles. So we have this new quantity. So from currents, we find the A, we find the magnetic field, we find this magnetic dipole, then we find the magnetization. Now, once we have the magnetization, we can define a couple of new quantities. So let's remember for a moment that in electrostatics, we had that the charge or the charge density, this was the source of a potential and the source of an electric field. Okay? This was for the electrostatics. But now in magnetostatics, the source for is going to be a current I, which is measured in amperes, or current density J, which is the current density or current per unit area. So any one of these two will serve as a source for the magnetic vector potential A or the magnetic field flux B. So the sources are right here. Now, we mentioned these because if you remember, in electrostatics, we had a dipole moment P, and this dipole moment P helped us to conclude or to define a new vector, which is the polarization vector. Now, similarly, we are having a magnetic dipole, which is helping us to define a magnetization vector M. And back then, we argued that in a system, if we have an external electric field, the different materials are going to activate or to restructure the electron cloud distribution by creating dipole moments inside the material. Now, because of that, so because of this polarization, which is different from zero, we can find a current density. So this was what we had before. Now, if polarization vector here is different from zero, we can determine the charge density because of the polarization in the volume. We used to call this one rho PV. At the same time, on the surface, we can have a charge density because of the polarization of the surface. So we can have rho PS, which is the charge density because of the polarization on the surface. And this one, we wrote this one as being equal to the polarization vector P dot product with AN. Okay? So this is what we define for electrostatics. Then for the charge density, because of the polarization in the volume, this would be equal to minus the divergence of the polarization. Okay? So this is what we wrote for the electrostatics. It's always worth to check the units, how the units depend, but it looks like if you check carefully, the unit of this row and the unit of this row are completely different, and it is obvious that the volume, the charge density per unit volume, it has one more inverse meter in the expression. So, because here we have 1/meter, the unit of this one, that's what it is, 1/meter. Now, we have this, which was for the electrostatics, and now similar structures or similar constructs, mathematical constructs, but they're not only mathematical constructs for sure, they will show up as new currents in the systems, which means that because of this magnetization, we can define a new current, which is going to be J, current density, because of the magnetization on the surface, which now it can be written as M, magnetization, cross product with AN. Okay, so this is how we can denote this. And we can also define the current density because of the magnetization on a volume, which is going to be equal to the current of the N, current of the magnetization. So having these two, this pair of results, which come in these equations, they are valid when the fields are in material medium. Okay, so we're dealing. When we have a material medium, we're not considering in vacuum because vacuum would be different. Vacuum would have no magnetization for sure, and in vacuum many things are straightforward. In Maxwell's equation, the propagation of electric field and the magnetic field is way different, and most of this is mostly portrayed because in vacuum we are dealing with mu zero and epsilon zero permeability and permittivity. And these belong only to vacuum or air, where air is pretty much approximated to pure vacuum. And this even concludes that the speed of electromagnetic waves is equal to the speed of light, or something which is approximately 3 times 10 to the power 8. Okay? And this is equal to 1 over square root of mu zero epsilon zero. So again, but these belong to vacuum or air, but these equations that we write here on top, they deal with the material medium. So in order to portray this one, so we started from the magnetic dipole here, let's start to portray this one, what this means. So we assume that a certain material, which we can draw this like this. So this is our material, and if there is some magnetization, we assume that we have a lot of dipole moments that go like this. So we have infinitesimally small loops where effectively there are some currents moving around. Those are the loops, and then if these are the loops, the direction of the magnetization or of the dipole is pointing out. Okay, so it's going to point out like this, and let's see the JMS. J becomes the magnetization on the surface. This is going to be equal to M cross AN, which means that this is AN on this surface is like this, and the magnetization is here. So if we use the right-hand rule, so the magnetization is pointing out of the board. We have this versus this, so we take the cross product, use the right-hand rule. We get a current like this, here, here, and here. So it looks like, if you look up at the material like this, assuming the loops are like this, we're going to have an effective current flowing as we are showing here on the board. And then it is worth noticing that the JMS, it has units of ampere per meter. This is ampere per meter, and the JMV is ampere per meter squared. This is the traditional unit of the current density, which is always equal to the current divided by the surface area squared, where if we can have, for example, a current which is 10 ampere through a wire that has a diameter of 2 centimeters, the current density, this is going to be equal to the current divided by the area, which would be 10 divided by the pi r squared. R is 1, so radius is 1 centimeter. This is 10 to the power minus 2 squared. So we are going to have a result of the current density of 1 over pi times 10 to the power minus 4 plus 1, 10 to the power 5. So this would be the current density, 10 to the power 5 divided by pi, and per meter squared. So this would be the current density, but this is just as an example to see how the units are related. Now, with this in mind, we come back here, and if you remember, when we discussed about the polarization in electrostatics, we also constructed a relationship between the electric field flux and the electric field intensity, which was the D and the E. So we made a relationship between D, so D was equal to an expression of E and the polarization. And here, similarly, we can construct a relationship which relates the magnetic field with the magnetization, sorry, the magnetic field flux with the magnetization. So here we assume that let me have a look here for a moment. We can say we can get that the curl of the magnetic field, this is equal to mu 0 times J plus J because of the magnetization on the volume. So in essence, we can say that an external magnetic flux density, we have the following. So D dot D external, this would be equal to mu 0 times J free. So this is the free current density. So we can write this like this. And this is the external. Then in this material media, because of this new exposed so the new magnetic field, it will be now the B external, which was the plus the B induced. Okay, so this is how B IND, it means that it's the B induced. This is the B, the total magnetic field plus total. Okay, so this is how we move on. Then we can also assume, not assume, but if we have a look at these expressions, in fact, so let's see what is this J and D. So this extra term, which is going to show up in this identity at the top. Let's have a look here for a moment in this material. So we have the same material, and apparently there are some effective small currents which are looping around in locally, and the magnetization. Let's assume that it's here M, 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 M. Now, if the material is uniform, which means that also the magnetization will be the same everywhere, then this B induced will be equal to 0. Okay? So we are saying again, if the magnetization is the same, the induced B will be 0 because this space gradient, or the del operator of the M, or the curl of the del operator with this, which in principle is a space derivative, d over dx, or whatever it is, this will be 0 if M is uniform around or across the material. If it is uniform across the material, then we have the, sorry, forget this, we have the curl of M, or the space derivative of the M, will be equal to 0. So this means that if you are ever considering this new term that will show up, we are assuming that a region which is not uniform for several reasons or several constructs, or we don't need to put an argument right now, but probably this material it's not pure everywhere. It has probably some low level of impurities or some different compositions, and that makes them having a non-uniform pattern, which results into a non-zero induced magnetic field flux. Now, let's see an example here. Let's have an example which we have to start with some classical examples right away. And let's assume that we have a cylinder. We have a cylinder which looks like this. And this cylinder, it has a length L or a height L, and we are given, we have an axial magnetization. So we are given that the magnetization is equal to AZ times M0. So given this axial magnetization AZ times A0, the question is to find the magnetic field flux on the axis, and more specifically, at some point, let's try to draw this a little better. So let's try to identify the magnetic field which is created at some point P away from this specific cylinder. Now this cylinder, this is filled up. It's filled with material, and since we have a symmetry, a cylindrical symmetry, we can use the coordinates R, phi, Z. Okay. So we are dealing with a cylindrical symmetry, and then we try to identify. So given these, the question is the following. B is what? Okay. What is the magnetic field? Only because of the magnetization given like that. And immediately we start looking at the expressions from which we can define the J. Because what we can do is that if we are given this magnetization, we can try to identify what is the current density because of the magnetization on the surface, and what is the magnetization, what is the current density because of magnetization on the volume, and then from these current densities we can find the magnetic field. Now this expression, this is equal to the curl of M. So if we look at this expression here, we get that this is going to be equal to the curl of M. Now, this is the curl of M, which is checking the rate of change per length, per unit length. And since M is a constant, so this M0 is a constant, this means that we get zero current density inside the material. So inside this volume, it's not drawn the best, we have no current flowing around, but we do have current density. Not we do have, we don't know yet, but the expression is this. We have to calculate the M cross product with AM. So let's clear out some of the material which is not very essential for the moment. Let's keep only the expressions for the current densities. And so let's try to identify here on this surface area, the normal AM is equal to AZ. Okay. Here on the bottom, AM is equal to minus AZ. And on the other side, so this cylinder, it has three surface areas, okay? Where the top side and the surface area, it is defined by the normal vector to it. So we can define a normal vector which is AZ. We can define another normal vector pointing downward minus AZ. And we can define another point vector which is AR, A little r, which is the normal components for the side here, like this. And then let's write this expression. This is equal to M plus AN. And we also know that A cross B, the cross product between any two vectors, is equal to magnitude of A times the magnitude of B times the angle sine theta. So we take the sine of the angle between the two vectors. Then we immediately try to identify or to write on the board the magnetization vectors. So the top area, the magnetization vector, is shown here in red with M. Here at the lower area, it's pointing up because it's M0 times AZ. And on the side, the magnetization is this. Okay? So when we look at this expression, it looks like on the top, the angle between the M and AN here is 0. So since the sine 0 is equal to 0, it looks like for the top, at the top, the current density, because all the magnetization on the surface will be equal to M AZ, M0 AZ, which is the M, cross product with AZ, cross product with AZ. And AZ cross AZ is equal to 0 because the cosine is equal to 0. So this is equal to 0. Similarly, the J, because of the magnetization on the surface, but at the bottom, we have here M0 AZ cross product minus AZ, and this will also be equal to 0. Now, on the sides, we observe that the angle between the magnetization and the AN is 90. The sine of 90 is equal to 1, which means that the current density, because of the magnetization on the surface area, this is a vector quantity actually, we should not forget that, this is equal to magnetization cross AN. The magnetization is M0 AZ cross product with AR. With a small r, and the magnetization with small r, we have, I often forget this, but we have the coordinates are r, phi, z. R, phi, z. And we know that if we follow the clockwise direction, we get, so here we have AZ cross AR, so the result will be M0 AZ cross AR. If we look here, we get A5. So it looks like the current density on the surface of this cylinder shape will be M0 times A phi, but let's not forget that phi is the unit vector which denotes the direction along which the phi angle is going to increase. So having a cylinder like this, the angle phi increases like this. So as we follow this path, the direction will be around in this way, which means that here we have our curve. Okay, so our curves will appear everywhere on the sides. Now we found what is the current density, but what is a little tricky is we need to figure out the currents. So we know the current density, and let's have a look. The current density, it has a unit of ampere per meter. This is very essential. That's why it's always good or important to write the units. It's not like the example that we just solved a few minutes ago, where the unit was ampere per meter square, but this is ampere per meter. Now, let's give an example just for a moment. So if you have a wire, and then when we find the current density, this is J is equal to I over area. So the area that stops it. So we divide it by this area here. Okay? But now that we have a very thin layer, the idea is that what is effectively here, this is the area that is stopping the current that is flowing through the wire, which is here ampere divided by meter squared. Here, the effective quantity, which is perpendicular to the propagation of the current, is this little vector here, or this infinitesimally small unit, which is pointing like this. So the current is circulating like this, and then here we have this is stopping, which means that the current density now, similarly to what we had here in the wire, the current density is going to be equal to I over length. And this length is going to be dz, okay? dz. Which means that if this is the current density, J is equal to I times dz, this means that equal to J, and the I, it has a direction for sure. And times M0 times dz. Okay? So that's the current. So now one way to represent this one is the following. We have current flowing everywhere. Okay? This is full, it's like water flowing across this cylinder, and it's going back and forth. Okay? It's a beautiful construct if you don't think about it. But now, what we need to do is that, so the tricky part is that how we're going to make use of this one. Well, to make use of this one, we know that we have the Biot-Savart law, and from the Biot-Savart law we can find the B and so on. But let's think for a moment how we can visualize this. In order to visualize this one, we can assume that we have very thin layers, not layers, but wires. Let's think that we have an infinitesimally small thin wire, which we're going to draw this in black. And so this is the wire, and this is carrying some current. But what is the current? The current is JDZ, which is given here. Then, right on the bottom of this one, there is another wire. Again, what is the thickness? The thickness, let's draw this one in red. So this is another wire. So let's assume that we have a lot of wires. So it's like a coil. Imagine that you have you want to construct a magnet. You construct a coil. So you wrap up a lot of wires like this, like black, red, blue, and all of these again, their thickness is dz. Okay, and then so we get here dz in blue, dz in black for sure, and we get also dz in red. Okay, so we just need to add up all of these. We have to add this, we have to add this, and we have to add this. Okay. So if we are adding up all of these, that means that we are effectively integrating over a lot of wires. We have covered an example which is very similar to this one, where we have solved before what is the magnetic field of a wire, and the problem when we solved it then, it looked like this. Let me erase this part. The problem it looked like this. We had a wire which was carrying some current, okay, I. This had a radius B, and at a specific distance, we found the magnetic field right here, right? So we have solved this problem before, and the magnetic field, it looked like something like this. The B, this was equal to mu0 times I B squared over 2 Z squared plus B squared to the power 3 over 2. So this is the magnetic field which is created only by a single line at some point up here. But now, all we need to do, so this is a magnetic field of only one stripe, of let's say the blue one. Then we have to add up the contribution of this magnetic field, which is the red one, and the contribution of the wire, which is in black. Which, so now, let's keep this one here, and these expressions here, probably these can stay, or we can write only here that this is equal, on the surface we have M0A5. We need this is M0A5, so let's keep this. This is a different expression. We can erase this because we made clear a lot of, we made this clear. And then the only thing that remains is to write down that since this I, so let's write this for a moment, this is equal to mu0 B squared over 2 times Z squared, where Z is the distance from the specific wire to the point of interest to the power 3 over 2. But I, we're going to read I, we have to multiply here M0 dz, right? Again, it's magnetization times the thickness. But since we have this infinitesimally small dz, allow me to write here dB. Okay? This means that since we have a very small, infinitesimally small wire in principle, this is dB. But what we want to construct a complete magnetic field, which is the integral of an integral. It means adding up a lot of wires like this. So adding up is essentially equal to the integral So then we can write here that the total magnetic field B is equal to the integration of dBs, and then we can put here also another integral sign. Okay? So the magnetic field that we're trying to find out here at this point, it is effectively B is equal to the integral of all these dBs, small magnetic fields, and we integrate also the side of the equation. Then we look for terms that are constants. So this is a constant, this is a constant. Here we have z, because we need to integrate over z. And let's assume that the point P here, the coordinates of point P, they are, the radius is 0, the phi, so radius is 0, phi is 0, and z, let this be z. So we want to find, and let's assume that the bottom of this cylinder is lying on the xy plane. Okay? And then this means that when we integrate all of these currents, where are the currents located? We need to integrate from Z0 to ZL. Okay? So this will be the limits of the integral. And then if we integrate these quantities, we need just to figure out a couple of terms. So here we have M0 dz, but then in this expression, we can still modify a little something very important, which is the following. Let's write this again, mu0 b squared 1 over 2, we're keeping this 2 out. We can even keep the m0 out, but let it stay here for a moment. And this is something that we need to modify a little. And the modification that we need to do is that this little component, it is found at the distance z prime, and the thickness is dz prime. Okay? So it's the type of language that we memorize. We say that at the height of z prime, we select the delta z prime thick element right here. So this means that how far is the wire of interest, or in this wire in red, how far is this one from the point here? So this is z prime, and the distance is, with respect to the 0, should be the z up here minus z prime. Probably, let's draw this one here better. So whenever we try to integrate over some quantity, we denote, we say that at the distance z prime, we select an infinitesimally small length element, which is dz prime. And with dz prime, we denote the prime where the currents are, for the currents, okay? And then in this expression, we are left with z minus z prime, because this is how far plus b squared. This is how far we are. So this distance, this is z prime, and this is z, and the difference or the distance from this element that we are considering, the current flowing here, from here to here, is z minus z prime. So we denote this one in red. So the distance here, this is z minus z prime. So this is the expression which should show up here. And the integral here is dz prime, we integrate from 0 to L. Okay. So that's the magnetic field expression. Now, being this, we just need, we get this integral from the table integral, and the final answer is going to be equal to, B is equal to, we look, B squared, we have mu0 m0, mu0 m0, times B. Let's look for a moment. We should have mu0 m0 divided by 2, and it looks like a couple of terms do cancel out. And what is cancelled out is in fact Let me think for a moment. So actually, so let's keep it like this: U0, M0. Let's keep here the B squared, and let's substitute L. So if we, no, wait a second. No, we cannot substitute it right away, but we should get from the table integral what the result is, and I think we can write the final answer right away. This is Z over Z squared plus B squared. This is square root minus Z minus L. Z minus L squared plus B squared, and this is also in a square root. Okay. Yeah. And this B squared is cancelled out somewhere. So this is how we find the magnetic field. So what we did not cover in detail is in fact this integral, which this is of the form Z minus Z prime. Yeah. So this is of the form integral of dx over x squared plus a squared to the power 3 over 2. So you can look at the table integral of this integral, what the answer is, and we can substitute the values. So this was regarding the how we can make use of these specific expressions. When we found that the J and B was equal to 0, and here JMS is equal to J cross AN. Now, with this example, we can, so now that this is clear for us, we can move to a next step, which will be, now that we know this J and V, we need to include this one into the expressions to relate the flux and the intensity the same way that we did for the electrostatics. So now, let's have a look here. We have the following. We have 1 over mu 0 times the cross of P, the cross product of P. This is equal to the J, the external, the initial current or the free current, plus the current density because of the magnetization in the volume. And this will be equal to J plus, so we should not forget that this was equal to the curl of M. So this is what the J and V was equal to. So we add this term here on this side, curl cross M or curl of M. And now what we can do, so this is the free initial current density. Okay, so let's put it with an F. And we just move, we can take this term to the other side, and we know that the derivatives, they are linear operators. Okay, so since they are linear operators, we can write here 1 over mu 0, or probably it's best if we factor out. So this is a constant. This constant, we can take it inside of the curl. So this is B over mu 0. Then we have the curl of cross product B over mu 0 minus M. So we take that this is equal to the J. Okay, and now this new quantity, we can define a new quantity which we call the magnetic field intensity H. So this H is equal to P over the permeability minus the magnetization. And this relationship between these three for sure is in the material media. If the magnetization is equal to 0, if we're talking about vacuum, then this remains, which is also true. But all of these, this is how they are related. And now, what we can do here is that, and the unit of this new quantity H that we have not seen this much, it's ampere per meter square. And let me think for a moment how. So we can attempt to write down so if we take the flux integral of the curl of H, this is, so just as a reminder, if you remember, we had the divergence theorem, which was something like this. The divergence of the vector field integral over volume, this was equal to the vector field H times ds. Okay, this was the divergence theorem. Divergence theorem. But we have also the Stokes theorem. And Stokes theorem, it states that the curl of H integral over ds, this should be equal to the integral of H dl. Okay, and this H dl. So this part is a Stokes theorem, so divergence theorem, it converts an integral over meter cubed to an integral over meter squared. And the Stokes theorem, it converts an integral over areas to an integral over meters. So I'm just denoting the units of these. And meanwhile, we know that this is a curl of H. What this is simply J, right? And J integral with ds is equal to I. So here we derive a new important quantity, which states that the integral of the magnetic field intensity over some closed loop, this is always equal to the curl. So here we have also an important relationship, which is called the Ampere's law. So this is the Ampere law, and again we discuss. We move into the discussion of what is next actually. So if you remember in electrostatics, what we did the following. We had the dipole moment, P, right, a small p. We found the polarization capital P. Then with capital P, we constructed the relationship between D, which was a function of the electric field and the polarization. Okay, we did this before. And then we said that whenever we have the polarization, this permittivity epsilon 0, it's not anymore epsilon 0, but it's going to be some epsilon r times epsilon 0. But this was the relative permittivity, and this was the vacuum permittivity. Now, these are the same steps that we followed in electrostatics that look like this. We have to do the same for magnetostatics. Now, the idea is that from mu0, we are going to define, this is for vacuum, another mu r times mu0, which will be the permeability in material media. And for this one, in order to do this, we define that the magnetization is equal to some susceptibility. This is the magnetic susceptibility times H, which in principle, this is psi H. So this can appear in this term. So this is called susceptibility. Magnetic susceptibility, and B then, B would be equal to mu 0 H, because, so if you have a look at this expression, if you multiply by mu 0 everywhere, we can write down that the mu 0 H is equal to B minus mu 0 M. So we have this, but this mu 0 M, this is equal to B minus mu 0, and the magnetization, this is psi M times H. Okay, so if we write it like this, it looks like we have on both sides, we have H's. So this means that we can construct the relationships of B with the H. So here we have mu 0 H. When we have this, let's take this to the other side, plus mu 0 psi M H. We factor out this again, and this is 1 plus psi M times H. Now this is the new relationship between B and H. So this term here, we call this one relative permeability. So this one, we call this mu R, which finally, this means that B is equal to mu times H, or mu R times mu 0 times H. Okay? So this is how, and this mu R, it does not have any unit, because in order to preserve the unit, this means that this is just some ratio. Okay? So it is a unitless quantity, it's just a parameter. And now, this relative permeability, this mu R that we define, this helps us to determine the properties of different materials. So materials, in terms of their magnetic properties, they can be defined as diamagnetic, paramagnetic. So we have a couple of important definitions. We have diamagnetic material. We have also paramagnetic material. And with these two types of materials, we have that this mu R here, mu R, it's smaller or very close to 1. And for the paramagnetic, this mu R, it's larger and more comparable to 1. So these are these two specific materials. And there is also some details regarding these two. For example, the diamagnetic material, it results from the orbital motion of electrons in orbit. Okay, so this is, so we have a charge and we have the orbital motion of electrons. So now we have an electron which is moving around the nucleus, and effectively this is creating a loop. Okay, so we have a current. If the electron is moving clockwise, we have a current counterclockwise, because we know that the electron moves in the opposite direction with the effective current. So now in diamagnetic, we have the electron's motion in the orbits, but in paramagnetic, we have electron spinning around themselves. Okay, so here, an important effect is this idea that if we have a pair of electrons, we have electrons that move in one direction or in another direction. So this is because of the spin around itself. And this is the effect which is dominant in paramagnetic material. And this is the spin across something, spin across nucleus. So one way to present this one is, for example, the diamagnetic is the rotation of Earth around the Sun. Okay, so we have, this is the star of our solar system, and here we have the Earth. Earth is doing this, okay? But then the paramagnetic, it can be compared to the Earth rotating around itself. So we are rotating around, Earth is rotating around itself, so we have the creation of day. So this is like paramagnetic and diamagnetic. If Earth rotates around itself and around the Sun, electrons do the same. They spin around themselves, and they also spin around the nucleus where they are located. Now, this is paramagnetic, diamagnetic, and we also have the ferromagnetic. Ferromagnetic. This ferro from Italian, it means like iron. So any material and this mu r in this case, it's a large quantity. So this mu r is much larger than 1. And what we can say here is that the ferromagnetic materials, they are used a lot to strengthen the magnetic field that is applied at in some region. And what is relevant probably that we can define here for ferromagnetic materials is that what they can do is that they can cluster. So if we have a certain material, what happens is that the magnetic dipoles, they can create clusters around that have all same orientation. Okay? So this happens, and sometimes they randomly change direction. What might let's also say this one: a ferromagnetic material, it is made possible when most of the dipole moments are oriented in the same direction. But what can happen is that there is a critical temperature, ECE, which is a Curie temperature, above which, so if temperature is larger than this critical temperature, then we don't have a magnet anymore. So the properties are damaged, or the temperature is so high that the magnetic moments are randomized. Okay, so they are not all of them pointing along a specific direction. So all of these are vectors and will add up. But if the temperature is too high, the local clusterization or the local coupling, maybe this is the better word. So these magnetic moments, they couple together and they create classes where all of them are pointing along a specific direction. And as you said, these are vectors, so they are pointing like this, they add up. But at a specific temperature, the temperature is so high, at this high temperature, it is considered to be high kinetic energy, and now they are random. So they rotate randomly because of the high kinetic energy reflected as a result of the temperature. And now that they are random, they don't add up to a net magnetization over large clusters inside the material. So that means that the magnetization is converged to 0. If you get a magnet and if you heat it up, it won't work anymore. So this magnet that which you can attach to your refrigerator, if you heat them up, it won't work anymore. So now here we discussed important parameters regarding the H and the D. Now let's try to predict what we're going to do next. Regarding what we're going to go next, it will be an important aspect, which is the boundary conditions. So let's try also to construct the material in a logical way, which is the following. We learn about B, which is a flux, okay? And now we define H, which is intensity, okay? And then, again, we always make relationships or equivalences with the electrostatics. And so this is magnetostatics. And the electrostatics, we had the D, which was a flux, and E, which was intensity. Okay, so this is how they are related. The next important step that we need to cover is the boundary conditions. Okay, Now, boundary condition. Now, you may forget a lot of things, but among something which will be the last thing to forget should be the following. That flux is a more fundamental quantity than the intensity. So we can write something like this. Flux is more important than intensity. Now, an equivalence with this principle is the same way that saying that the energy is much more important than linear momentum, or is much important than the force. Why is this? Because the linear momentum is the derivative of energy with respect to the velocity, and the force is the derivative. So if we take here d over dv, we get the linear momentum. If we take d over dt, we get the force. So now, this is what we mean with flux is more fundamental quantity than intensity. And now that we know this, we can always say that if we are passing over two different mediums, so let's assume that this is medium 1 and this is medium 2, and if we have a magnetic field which is incident like this, and assuming that the properties are different, if the properties are different, we will have that the normal components, so flux, which is the V, flux perpendicular 1, it should be equal to flux perpendicular 2, which means that the normal components of the magnetic field, they are conserved. Okay? So we care about, so this is about the boundary conditions. So this is flux and flux perpendiculars, they are conserved. And it is difficult to be a conserved quantity when you are moving across this path, okay? Because here you observe a barrier. You have different properties. The material, the magnetization might be changing, or this could be air, this could be a metal, or this can be a ferromagnetic material. So to be conserved, if you are moving from here to here, it's very difficult. But essential quantities like flux, they can do it. Okay. The same thing happened also for electrostatic field. We also had that for this flux, we have the D1 perpendicular. This was equal to D2 perpendicular. So in medium 1, the perpendicular quantity was equal to the perpendicular quantity in D2. So it doesn't matter for fluxes if they are changing a medium, which is I don't have different colors, so from here to here. But now, what happens for intensities? For intensities, we have the H1, but the tangent component, which is this component. So let's draw the intensities in a different color. So this is an intensity, and this is also an intensity. And let's do it also like this. So intensity is a weak quantity. So intensities, when they go from here to here, they cannot be conserved. Okay? Because, so this H in medium 1, the tangent component, which is this, is going to be equal to the intensity in medium 2, but still only the tangent component. So now, why is it is easier to be conserved why is for the tangent components easier to be conserved? Because moving from this point to here is not something very essential. Moving from 1 to 2, that's difficult, so only flux can do that. But intensities, the best they can do is this. So next topic is we have to prove the boundary conditions, which essentially, even without proving, using only intuition, we expect from all of you to know that fluxes, perpendicular fluxes, they are conserved, even though we change different medium. And tangent components, intensities, this is the best that they can do. The same logic, it was also for electrostatics. Now, this was the general idea regarding the boundary conditions. We'll keep it, we'll stop for now, and we'll continue in the next session.